Based on the test results that we have, the armor deck panel would be suitable for any kind of floor system because of its stiffness and high load carrying capacity. Every aspect of the panel is incorporated into the manufacturing process, so when it comes out of the form, it's complete, including the anchorage plates that are all part of the forming process. If the panel requires the tactile detectable strips on the edge, they're incorporated into the form. They're integral to the system. The test protocol for this panel was developed primarily by WJE in conjunction with discussions with Engineered Plastics. The product components, how they were put together, and how the product was made to give us an understanding of what's inside this panel that we were going to receive. We developed the test protocol, and we developed the vibration test protocol, the load test protocol, the uplift force, and the uniform load values. The first test that we did on the armor deck panel was a vibration test. The purpose of the vibration testing was to verify that vibrations on the panel would not be larger than anticipated on a normal concrete panel. There are ANSI guidelines for allowable vibration levels or perceptible vibration thresholds. Being a lighter weight structure than normal, we needed to verify that the vibrations on the platform did not exceed those perception thresholds. People standing on the platform would be disturbed if, while they're standing there, people walking behind them produced a large magnitude of vibration. So we needed to verify that those vibrations were not excessively large. And the testing that we did showed that the vibrations on these panels were no larger than walking on a similar concrete panel. We set up the panel in the lab, measured vibration response due to small impacts to determine the resonant frequency and the damping characteristics of the panel. Then we had people walk across the panel in a designed pattern and measured the response of people walking on the panel, both in a unloaded and a loaded condition, where the loaded condition was 100 PSF, uniform load. We achieved that load by setting lead ingots across the panel surface, leaving a traffic pattern for the people to walk through, and we measured the dynamic response as they walked across the panels. One test that we did in the field was a side-by-side vibration comparison test on a metro station in Hazel Crest, Illinois. Engineered Plastics had installed one of their armor deck panels in a metro station that was planned for renovation. They installed it in between the existing concrete panels. And I went to that station and I measured vibrations that were produced by people passing, walking over the panels, and vibrations produced by passage of a train to demonstrate the difference in the vibration between the armor deck and the concrete panels. The results of that test indicated that there was no significant difference in the vibration characteristics. The train passage produced essentially the same magnitudes of vibrations on the concrete panels as the armor deck panels. The next test after doing the vibration testing was to do a load test on the panel, applying a uniform load in increments up until we actually failed the panel, got it to collapse. We applied these loads in 25 PSF, pounds per square foot increments, up to a uniform load of 300 PSF. The design load, or the intended uniform live load that should be applied to the structure is 100 PSF. Our intent was to load it to 3 times that amount and verify that it could take that load safely with a minimum amount of deflection. We ended up applying a load of 600 PSF to the panel, and we still couldn't get it to fail. So it basically was 6 times the allowable design load. As far as a design criteria, the allowable deflection is supposed to be 1/240th of the span. And we calculated that the allowable deflection at 250 PSF, which was the design allowable live load should allow a deflection of 0.54 inches, and the magnitude of deflection that we had at the 250 PSF load was actually 1/8 of an inch, so 0.12 inches instead of 0.54. We calculated that out to be 24% of the allowable deflection. This panel was impressive in how rigid it was. The fact that we were able to load it to 600 PSF and still had no significant deformations, no failure of any element of the structure was impressive. During the course of the load test, when we applied the total of 600 pounds per square foot load to this sample that we had mounted in the lab, we held that load for 12 hours. It was a combination of the lead weights and the vacuum chamber that we were able to achieve that 600 PSF load, and we held that for 12 hours. During the course of the entire test, we were measuring the deflection at the mid-span and at the support points and at the overhang points on the panel. The intent of this duration of this applied load was to verify that the material didn't creep while the load was held on it. And then at the end of the test, we monitored the deflection for another 24 hours to verify that the material did or did not return to a 0 point. It turned out after applying a 600 PSF load, the permanent deformation that had been set into the product was 1/8 of an inch, and that 1/8 of an inch remained after another 24 hours. The design criteria for a load test on such a product would dictate that the permanent deformation not exceed 1/4 of the total deflection, and we achieved a much better recovery than that. We performed in the lab slip tests based on an ASTM standard test method with a standard slip device. It's a small weighted sled that has a texture on the bottom surface where it comes in contact with the product that's to be tested, and it's placed on the sample, and one measurement is taken on the force required to pull this test rig across the sample, and then the product surface is wetted with water and the test is performed again. And so there's a comparison of the dry and wet forces required to pull this weighted sled across the sample.
In 2005, Armor Deck transit boarding platform panels underwent testing with Underwriters Laboratories in Chicago. The purpose of this testing was to collect thermal data to ensure the panels met the requirements of the Chicago Building Code. The testing was conducted in accordance with ANSI UL 723 to simulate fire exposure conditions that might occur on an elevated transit platform. The test ran for 1 hour and consisted of a 48-inch by 48-inch section of armor deck situated on top of a blast furnace with open flame, which maintained a temperature of 1700 degrees. Armor deck maintained a zero flame penetration and produced only a 3% rise in top surface temperature of the allowable tolerance, while simultaneously withstanding a 500-pound static load. The armor deck panel was then removed from the furnace, and a 1,000-pound static load was applied with no deflection.
Our laboratory test on the full armor deck panel took place in 1999. In 2005, Engineered Plastics came back to us to ask us to review our test results and comment on how those test results compared to the City of Chicago load test requirements. And in that process, we noted that we applied loads that significantly exceeded the requirements of the City of Chicago test. And the sustained load that we held was much larger than the requirements of the city test, which would have been 250 PSF. We held a load of 600 PSF, but we only held that load for 12 hours, where the City of Chicago required that the load be held for 24 hours. because our test protocol didn't exactly match the city test protocol, they required that we do design calculations, or load capacity calculations for this panel. And in order to do that, we had to get material properties. The two in particular that we needed for our calculations were the tensile strength and the flexural strength of the product, the strengths of those elements. So we had engineered plastics cut up a sample panel test specimens to do flexural tests and tensile tests. The original testing was intended to show the load capacity, or demonstrate the load capacity of the armor deck panel. And the subsequent testing that we did was to support the calculations that we were doing to determine load capacity ratings, what the city of Chicago was asking for to satisfy that requirement of the city.